Hello everyone, this is Subhabanik. I am an analog and mixed signal layout engineer and welcome everyone from Canada, British Columbia. This is my lecture number 2 with analog electronics, and in this lecture I will cover some most important basics for MOSFET. I will not go too much deep, but I will cover everything, whatever you need to work as a professional engineer for the beginning level, as well as this basics also helps you to get your first job. First of all, I want to share you that this is my first video where I discuss about common source amplifier with active load and diode connected load switch degeneration, and also small signal model is input output resistance, everything. So this video is very useful for you, so whoever missed this, so you can watch this video also. So let's begin now. So if I tell very fundamental points about MOSFET is that MOSFET is a terminal voltage dependent current source. And one more point, it is a non-linear device. So usually someone may ask you in your interview, MOSFET is linear or not, but please be remember, MOSFET is a non-linear device. Okay. And there are basically two types of MOSFET, NMOS and PMOS. Although the properties of these NMOS and PMOS are same, I mean the operational reasons and point, and everything is same, but there is a little bit difference about NMOS and PMOS, which is that it always carry a negative sign. Let's say whatever true for NMOS, if you just add a negative sign for PMOS, it will be accurate, or we can consider a absolute value. Then it's no matter it's negative or positive, or NMOS and PMOS, whatever I will discuss is same for everything. So here I will consider an NMOS and discuss some important points. First of all, it has 4 operating regions. Obviously, the first region is cutoff, then it is in triode mode, then saturation. But there is one more region which is known as sub-threshold mode. And basically, engineers sometimes keep some transistor in sub-threshold mode to save some power consumption for the low power design. Okay, so what is the cutoff? Cutoff mean is nothing but whenever our transistor is off. So what is the condition of turn on a MOSFET? The condition is this: the gate to source voltage should be greater than its threshold voltage. Whenever its gate to source voltage is greater than its threshold voltage, then the MOSFET will turn on. And whenever the VGS is greater than VTH and my VDS is less than its overdrive voltage, then MOSFET is in triode mode, and at this point, MOSFET acts as a resistance. I will discuss later about this point. And the most important reason is saturation region, where it is mandatory for analog engineers to keep MOSFET in saturation mode whenever we are making any amplifier or something like that. For example, current mirror amplifier, whatever. So what is the condition of that? Again, the VGS minus VTS, the MOS should be on, and its VDS should be greater than its overdrive voltage. So in this reason, MOSFET act as an ideal current source. Not ideal. I will discuss in a separate video. Due to the general length modulation, it's not an ideal. I will discuss it later. And but then that comes to it when it is in sub-threshold. Whenever VGS minus VDS is whenever VGS greater than VTH, the transistor is on, and VDS greater than VDS minus VTH, which is also known as overdrive. This condition is also true, and still, one more point: VDS, the drain to source voltage, is less than its threshold voltage. It's mean VD, this value is negative. Okay, you can calculate some If you can assume some numerical value, then you can assume that uh, this term will be negative at this term at this point. So in this region, it is called as subthreshold mode. But although it's not important, sometimes designers make in this region to save some power consumption. But most of the time, in industry, we prefer to keep in saturation mode. So we are more interested in saturation mode. Yeah, whatever I said, BTS is also known as its overdrive voltage. So before jump anything, uh, whenever I was a student, I saw that most of the students are interested is VDS versus ID card, VDS versus ID card to illustrate its operating point. Most of the students are not concerned about this curve. Therefore, I kept this curve in first in my lecture. So before jump anywhere, uh, one more point is that most of the students also don't know why engineers are concerned about this two curve. So first of all, I want to explain the advantages. So why we need to learn VGS versus ID and VDS versus ID both curve. Well, there are lots of points, but here I want to make two point I want to mention there. It is that first of all, the analog engineers they need to find the appropriate bias voltage. I will discuss later why biasing is important in a separate video, but for the time being, the analog engineers need to find out an appropriate bias point. Why? To maintain the proper gain margin, slew rate, phase margin, or stability, or it also related to pole and zero, its gain bandwidth. So there are lots of properties. So therefore it's mandatory to set our operating point it define bias point. And this bias point they can find this curve, BGS versus IT, as well as as I explained already that we need to cap our transistor in saturation mode. So we have to find this common mode range actually. So the terms I am using here, slew rate, gain margin, phase margin, it may be unknown for some students or may be familiar for other students, whatever. I will discuss each and everything in my upcoming lectures, what these terms are and why and how we can do that. For the time being, just know that it's some property of a circuit. So to maintain or to achieve this circuit, we need these two curves. Okay. For example, we also need to find the common mode range. To find common mode range for any operational amplifier, for example, two-stage op-amp or fully cascade op-amp, we need this curve. However, there's also a point for power consumption, in which point is more appropriate for me. For example, as my first lecture, I discussed about some common source amplifier. From common source amplifier, you know that the gain is GM R out. Whatever the R out, you can see there's one tuning parameter. If I want to play with the circuit, then I need to play with its W by L, its ID, right? Isn't it? For example, it is a formula of GM. I will discuss it now. So if you want to play with GM, so you need to know how we can increase GM, how we can reduce GM. And there's also lots of pros and cons. So we will discuss it later. But for the time being, to just let you know that if you want to play with this circuit, then you have to know that what should be the appropriate bias point. For example, this curve is VGS by ID. And from this curve, as I explained, that MOSFET is a non-linear device. It's not linear like resistance. So you can see if my VGS is 0.5, then ID may be 10 micro. But if VGS changes little bit, 0.5 to zero point 0.8, then ID which increase more higher, maybe 3 times or 4 times. So if my ID increase, my GM will increase. We can see from this formula, right? So if my GM is increase, my gain eventually will increase. Obviously, there is some lots of trade-off we need to consider. I will discuss it later, but for the time being, just know that if you want to play the circuit, you know this card very well. Okay, so now let's see first the what is. Okay, okay, this curve is the BGS by ID curve, and you can clearly see that there are two voltages basically, BGS and BDS. So first of all, we need to keep constant one voltage. If we keep constant VDS and if you vary the VGS, we can find this curve. Okay, obviously this BDS can be 1 volt, 2 volt, anything. But if my VDS increase, this curve turn left in upper side. You can see in my curve here. So until VGS reaches VTH point, so the MOS will off, and in practical there flows some nanoampere current. But whenever my VGS is greater than VTH, means MOS turn on, then you can see there is a significant current flow through my drain terminal. Okay, and from this curve, we can define transconductance, which is opposite of resistance. Okay, so how can I calculate that? Uh, but okay, the unit for transconductance is Siemens, and in an interview, obviously, they will ask you about transconductance and how you can derive it. It may be in written exam or in interview, wherever. It's very important for job preparation. Okay. Okay, it's an nonlinear curve. To find its GM, so we need to consider a little bit portion. So a little bit portion means its derivative. So what is GM? GM is derivative of ID divided by derivative of BGS. And as I told you, as it is opposite of resistance, so it is known as transconductance. Okay, and there are three crucial formula, and you have to remember this formula, because in interview they may ask you, right, a formula of GM. Okay, so you have to remember this formula. Even if in written exam they may ask you to derive anything from this transconductance of any formula, so it is very important. As I also explained in this video, that why you know this formula. If you know this formula, then you know which parameter is related to what, and you can play with the circuit. So please note down this formula. And here I also explain, as I told you, that I am interested in the saturation mode, because most of the time we kept transistor in saturation. So this is the ID equation. This is the ID equation in saturation. Obviously, I am considering here there is no channel length modulation. And from this ID, just some, you can pause my video, and if you see, there is some basic calculation. If I take ID divided by VGS, if I derivative ID with respect to VGS, so we can find that this is the basic calculation, right? So there is nothing to explain. So you can find one of the formula here. Okay, and again, uh, from we always start from this formula, and if you start from this formula, and if we do some numerical calculations there, so we can find this term there. So from here, what do you know? We can see that VGS is nothing but like this, right? We can use this. So from here, I just put this value in here. So if do some numerical calculation, so we can calculate this one, right? How it comes, this formula, right? If you are interested, so I put it here. Again, always we start from this formula, and we know this term is nothing but GM, and we also can derive this formula, right? So I already told you why you need to find this, because without GM, if you want to increase the gain or its gain margin, is what can I say? Is gain bandwidth. So you need to play with GM. So to play with GM, you need to know how we can increase GM, the relationship with ID and GM, the VGS. Basically, VTH is constant, right? The mu and CUF, which is also constant. So your playable tunable parameter is only W by L VGS, right? So yeah, you can find the relationship from here. And yeah, now if you just consider this, this is the most popular one, if we just kept constant the gate voltage, and if you just play with the drain voltage, you can change the drain voltage, then we'll find ID versus VGS. Here my VGS is constant. And you can see if I increase VDS, my curve will shift in upward, or can I say it shift in left side. Okay, you can see in here. Basically, this point is pinch off when my transistor is off, and whenever it turns on, so it goes linearly, and whenever my VDS is equal to its overdrive voltage, this point is also known as pinch off point. After that, if we still increase my VDS, then the curve will saturate it. Okay, saturation means it works as an approximate ideal constant current source. But if you zoom in this area a little bit, so we can see it's not ideally constant, it's an upward trend. So in my later video, I will discuss that how channel length modulation affects. Basically, it happens due to channel length modulation. Okay, just let you know, sometimes the interview or in the exam, they may ask you that why this curve is not a flat line. Flat line means why it is not constant, why it is a little bit upward due to the channel length modulation. Okay, whatever, we'll discuss it later. And yeah, just let you know at the linear region where MOSFET is working as a resistance. And here, this is the equation of ID. I'm not interested in that. And in saturation mode, this is my current equation. But just let you know, this is the equation of ID. In my later video, I will also discuss that how we can use a transistor as a resistance, how we can use a transistor as a diode, as a current source. At that time, I will discuss about these formulas and is useful meaning in my later video, right? Okay. Yeah, and I also explained you the why we are very concerned about this two curve, and I think that it is now crystal clear you that why we are learning this curve. Okay, without motivation, without know anything, just remembering. And if we know any application, the why we are learning it, I think that it's more, we are more interested in this point. Okay, if you know the application. Okay, this end for now. So just if you like my video, just share it with your friends, and you can also comment if